Good afternoon, everybody. It's MrDoTheMath here, and today we're going to talk about right triangles, special right triangles. All right. So the first one that I want to introduce you guys to, and for our class, we'll be reviewing it, right, is the 90-degree triangle. Right. It's also known as an isosceles right triangle. One of my students asked me last period, like, how do I know if I'm dealing with a 90-degree triangle? Well, there's three things that can happen. Either you'll see that it's isosceles like this in a right triangle, you know it's 45, 90, or they'll give you the congruent marks to let you know that this has to be 45, 90, because the interior angles, the sum of the interior angles of a triangle is what? How many degrees? 180 degrees, right? Or you'll get this situation where they just say, hey, that's 45 degrees, right? 45, 90. The difference between 45 plus 90 is going to be another 45. Well, the difference between 45 plus 90 and 180, right? So this is how you know you're dealing with a 45, 90 degree triangle, right? Okay, now here's what's special about them, because they are special, right? Usually when we try to find the measure of the lengths of triangles, especially right triangles, we use what theorem?
About that.
We use Pythagorean theorem, right? A squared plus B squared equals C squared, right? And then we go through this long dance to figure out the A's, the B's, or the C's, right? Right. However, with the special right triangle, there's some rules, or there's some knowns, all right? We know that these are called the legs. The sides of the triangle that make up the right angle are called the legs, okay? And we know that the longest side is called the hypotenuse. The hypotenuse. Now, the sum for the measure of the hypotenuse is always going to be the measure of the leg times the square root of 2. All the time, all right? So, if we were ever given the measure of the hypotenuse and it was in terms of, if it was rational, and you had a leg times rad 2, you would just take what's in front of the radical and put it here. That's the leg, okay? So the hypotenuse, so you put this in your notes. Hypotenuse equals the measure of the leg times the square root of 2 every time, okay? So let's look at this example here. So in this example, if I said that the measure of this leg is 4, and that's all they gave you, using this rule here, we know that because these are congruent, this has to be 4 too. Right. And this being the hypotenuse, the long side, would be the leg 4 times the square root of 2. Right. That's it. You're done. You found the measures. Okay? This is how I can prove that this works for us. All right? If we didn't have 4 root 2 and we didn't have 4, because we know that these were two were equal, and we use Pythagorean theorem, we have 4 squared plus 4 squared equals C squared. 4 squared and 4 squared are what? 16. 16 plus 16, 32, right? Mm-hmm. And then you take the square root of 32, you get, what's that, 2 times 16? Yeah. 16 is a perfect square, right? Square root of 16 is what? 4 root 2. So, you see, we took the long way to get it, and then if you just know the rules, that's all you gotta do. Boom, just like that, okay? Now, what if we said, hey, your right triangle, and it's isosceles, and the hypotenuse is 7 root 2. What would the measures of the legs be? 7, right, because this is the leg, and this is just the root 2 part of your hypotenuse. So these sides are 7, okay? Now, here's where it gets interesting, okay? What if we said the hypotenuse was not 7 root 2, but just 7, okay? if the hypotenuse, if ever you get a hypotenuse and you get a whole number for the hypotenuse, the legs will always be, so for the legs, so if you get a hypotenuse that is a whole number, so when a hypotenuse is a whole number, right, the leg equals the hypotenuse times the square root of 2 all over 2. All the time. Okay? All the time. So, in this case, this is 7. Right? 7 is the hypotenuse. The hypotenuse is always defined as the leg x times root 2. And so if we're trying to figure out what x is, because that's what these are, we would go through our algebra, right? You got to get x by itself by dividing both sides by 2, and you end up with x equaling 7 over the square root of 2. But as we learned, we can't leave a solution in the terms of a radical 2, right? We can't have a radical in the denominator. So we got to multiply the top and the bottom by that radical. When you do that, you end up having 7 root 2 at the top, and root 2 times root 2, which is root 4, and root 4 can simplify to be what? 2. So you get 7 root 2 over 2. Now this is the math behind this particular rule. Okay? That's the math behind that particular rule. Okay? Let's look at another example. Let's try again. Alright? So, again, what if I have a right triangle like this, and I say the hypotenuse is 13. What would the legs be? 13 root 2 over 2. 13 root 2 over 2.
That can't be simplified no more.
I don't know. Can 13 root 2 over 2 be simplified anymore? Why not?
13.
Right. So 13 is odd. It's not even. Okay? Good. What if I give you this as a leg? What if I say the leg is root 3? If I say the leg is root 3, what's the measure of this other leg? Root 3. What's the measure of the hypotenuse?
Root 3, root 2.
So root 3 times root 2. Very good. This is the leg, and the rule is it's the leg times square root 2, right? So then you just simplify this. We just learned this. What's the square root of 3 times square root of 2? Square root of 6. That is your hypotenuse. Okay? Yes, sir.
Would it be wrong if you
This one?
Yeah.
Can you reduce this? Can you simplify this? Let's look at it. 6 can break up to be 2 and 3.
Oh, wait, no.
We don't have any pairs, so it'll just be the square root of 6. Okay? Good. All right. Any more questions about the 45, 45, 90 degree triangle? So, that's it for your 45, 45, 90 degree triangle. Next, we're going to look at 30, 60, 90 triangle.